record on this computer. I will share my iPad screen with you. And this time, Johnny on the spot, I remembered to put my iPad on Do Not Disturb. So hopefully this time we won't be getting silly GIFs popping up in the middle of our lecture. Okay, so now, come on. All right, we're going to do this again. Fantastic. Unplug, replug, reshare. Aufgezeichnet. Wonderful. All right, so last time on Monday, we were addressing the general problem of the probability distribution of the number of particles occupying each available discrete energy state in a quantum mechanical system. Wow, that was a mouthful. Okay, and so again, we have discrete energy levels. Epsilon 0, epsilon 1, epsilon 2, yada, yada, yada. We throw in some particles. Okay, and then our goal, as we said, was to predict the average occupation of each energy level. And similarly, we can get the average total occupation of the system, or the total number of particles, just by adding all of those together. All right, so now what we showed was that the answer that you expect for this is very general. It only depends upon the fact that there are discrete energy levels. It doesn't depend upon what those energy levels are necessarily, other than the actual numerical values. And the expressions that we derived depended upon which type of particle we were discussing. All right, so we showed that for fermions, that is particles with half integer spin, that they obey the Fermi-Dirac distribution. Okay, and the Fermi-Dirac distribution is that the average occupation of the alphth energy level is equal to, now let me make sure I write this down correctly, e to the beta epsilon alpha minus mu plus 1 in the denominator, like so. So that's the Fermi-Dirac distribution. And as we showed, what this thing looks like is a step function. So on this axis we have energy, and on this axis we have average occupation. Its maximum value is 1 because they are fermions, and there is a cutoff here set by the chemical potential, or the Fermi energy. Okay, and at t equals 0, what this thing looks like is the following. It's just a step function where all states below the Fermi energy are occupied and all states above the Fermi energy are unoccupied. Ah, how convenient that my U's also look like N's. Wonderful. All right. So that's the Fermi distribution at this is at t equals 0. And as you ramp up the temperature, green, the function just gets smoother and smoother. Okay, so that's T1. And this time I'm going to be careful to try to draw it correctly. That's T2. And when it gets really hot and spicy, it's pretty smooth. So that's T3. Okay, so all of these curves cross where the Fermi energy is, where each of these average occupation numbers are equal to a half. That is half probability to find a particle in there or not. All right, and again, the width of the smooth region, let's draw it for the orange one. The width of this region over which the function changes smoothly is on the order of kT. So the lower the temperature, the shorter that region is, and the more sharply it drops off. All right, the other kind of particles we talked about were the bosons. All right, so the bosons are the particles that have integer spin. Okay, and they obey the Bose-Einstein distribution. All right, and we showed last lecture that the Bose-Einstein distribution for the average occupation of the alpha-th energy level looks almost exactly the same as the Fermi-Dirac distribution. The only difference is in the denominator, you have a plus sign instead of a minus sign. Okay, so that is the Bose-Einstein distribution. And I didn't even try drawing this thing because we're going to talk about it in significant detail starting a little bit today and in excruciating detail on Friday. And so that's when we'll draw what this thing looks like. All right, now the last thing we showed when we left off on Monday was that both of these functions, so at high energy levels, so when we look at the occupation of high energy E alphas, that is low occupation, that they both look just like the Boltzmann distribution. Okay, so in other words, at high energy or a low number of particles, you can't tell the difference, but you know, whether it's a quantum gas or not, who cares? It looks the same as a regular classical gas. Fabulous tune, by the way. And so it's only when you get down to low temperatures and potentially high occupation states that the quantum nature of the system becomes apparent.
Professor?
Yes, please.
Both equations that you wrote look exactly the same.
Ah, that's because I am a silly goose. Yes, you're absolutely right. So that in the Bose-Einstein distribution should be a minus sign instead of a plus sign. Thanks for pointing that out. Honk. All right, everybody good? All right, good. So now what we're going to do today is to take these distributions and actually apply them to an actual specific problem to get a sense as to how a gas of quantum particles behaves. All right, and so the gas we're going to start working on is our favorite gas, and that's just where you take a bunch of particles and you stick them in a box. All right, so we're going to look at free, that is non-interacting particles in a box. Okay, so everybody's favorite gas from statistical mechanics, because this is essentially what we've been talking about all quarter, is how to understand the behavior of a bunch of particles in a box. It also happens to be, if you've taken quantum mechanics, one of the first problems you get introduced to in quantum mechanics and how to solve the Schrodinger equation. And so now what we're going to do is today we're going to take our pen and we're going to take our pineapple, that is statistical mechanics and quantum mechanics and statistical quantum mechanical mechanics, PPAP. All right, so here's our problem. We have our box. So here it is. It's a three-dimensional box. And without loss of generality and just to keep things simple, I'm going to say that all the dimensions of the box are the same of length L. Okay, consequently, the volume of our box is L cubed because it's a cube. All right, and again, we're going to talk about free particles. That is non-interacting, that is zero potential. All right, so the potential inside the box is 0, and the potential outside the box is infinity. So the particles may not escape. They are stuck in the box forever. All right, now into the box we are going to throw a bunch of particles, just as we have done previously. So there they are. Okay, so there's our particles. Now our job is to determine the statistical behavior of this collection of particles. The difference now from what we've done so far is instead of assuming that these particles are classical, we are going to assume that they are quantum mechanical. Okay, so in other words, we're going to assume that the particles obey Schrodinger's equation. All right, so we're also talking non-relativistic. All right, so their particles obey the Schrodinger equation. You have to get your umlaut in there. Okay, which implies they're quantum mechanical and non-relativistic. Okay, so now you got to go back and remember quantum mechanics class. And again, one of the first things they taught you how to do in quantum mechanics class was to apply Schrodinger's equation to determine what the wave functions of a particle stuck in a box look like. All right, and so from quantum mechanics, I'm not going to go through it because I assume you've seen it before. So from quantum mechanics, we know free particles in a box have plane wave functions. Okay, specifically, we know that, so the wave function psi in general is going to look something like this. 2 over L to the 3/2 sine 2 pi n, I will call that nx over L sine 2 pi n y over L y sine 2 pi n z over L z. And or cosines, depending upon exactly what your boundary conditions and where you put the origin of your box and all that good stuff.
So you missed an X. You're missing an X.
I missed an X. Silly me. Man, I'm really on a roll today, aren't I? X. There it is. All right, so those are our plane wave functions for a particle in a box, where these nx, ny, and nz are integers. All right, so they can take on any value from 1 to God knows what. I don't believe they can take on 0, because if they're 0, then you get 0, and then they're not there. So I believe the first n it can take on is 1. All right, so again, so what I've written down here is in terms of signs. Again, depending upon your boundary conditions, you may instead or in addition get some cosines. And so in general, a compact way to write these that takes into account both possible plane wave solutions, compact way to write is just that psi is equal to 1 over L 3/2 e to the I k dot r. Okay, so here I'm just taking the sines and the cosines and combine them together using Euler's identity to write them just as an exponential. And then depending upon what your boundary conditions are when you actually solve your problem, you'll get rid of one or the other. But in general, that is the solution. Okay, so now, as usual, r is your position vector that tells you where the particle is. Well, not where the particle is, which point in space you're talking about. Okay, and k is the wave number vector, which is equal to 2 pi over L in x, in y, in z. Okay, so this is the wave number vector. Okay, and so I can also succinctly write this just as kx, ky, kz. Okay. All right, so those are our general wave functions in terms of our wave numbers. And now hopefully you also remember that you can determine what the energies of these particles are in a box. Okay, so with energies, and the energies are equal to h bar squared k squared over 2m. All right, so you may remember that in quantum mechanics, the momentum can be expressed as h bar k. So this is the just exactly the same thing as p squared over 2m. It's just the kinetic energy of the particles. All right, and so again, this k squared is just the modulus of the wave number vector. So it's just kx squared plus ky squared plus kz squared. All right. Okay, so that's just basic intro quantum mechanics. So hopefully you guys are all familiar with that. All right, so now is when we start trying to take these solutions from quantum mechanics and apply them to the same kind of reasoning that we've been doing for statistical mechanics. Now, you'll remember back when we talked about the microcanonical ensemble, what we were interested in was all the different configurations of the position and the momentum that will give us the same energy level. Right, so we had this drawing of phase space where, you know, with a constant momentum vector that describes a sphere in your phase space, and then what we were interested in doing was integrating over essentially the surface area of that sphere to determine the number of available states. So we want to do exactly the same thing here, except using this as our expression for the energy, instead of p squared over 2m. All right, so now what you can see is that the energy is directly proportional to k squared. Okay, so in other words, all k vectors with the same length give the same energy. Okay, so just as before, when we started introducing the microcanonical ensemble and we drew our phase space with the momentum components as our coordinate axes, we're going to do exactly the same thing here, except we're going to use the k components instead of the momentum components, but they're more or less exactly the same, just off by h bar. All right, and so now the phase space that we're interested in is the k space, the wave number vector space. All right, so here's my phase space. I'm going to put kx, ky, and kz. All right, and so the fact that the energy is equal to h bar squared k squared over 2m means that all k vectors in this space that have the same length are going to have the same energy. So again, the shape that we're going to get from this, if I can draw it, is a sphere. Oh God, that's awful. Let me try again. Marginally better. All right, so there's my sphere. Let's do this to make it obvious it's a sphere. All right, so there's my sphere. My sphere has a radius equal to whatever value of k it is that I'm talking about, right? So all values of k that have the same magnitude lie on this sphere. All right, and so now what we're going to do is exactly the same thing we've done previously. Is what we want to do is to calculate the number of states that live on the surface of this sphere. And to do that, we're going to take the volume of our radius of our sphere, kick it out a little bit so that we get a volume that we can actually integrate over, and then just integrate and count the number of states inside that spherical shell. However, things are a little bit different now. Now, why is that? Okay, so now the problem is that k can only take on certain discrete values. Okay, so again, K, so let me write it like this. Kx, the x component of K, is equal to 2 pi nx over L, where nx can be some integer. So on and so forth. And same for the other components of K. All right, so now if I, for example, I go back to my phase space here, and let me just draw one of the plane. Let me draw the Kx, Ky plane. Okay, so I'm going to draw Kx. Well, it doesn't matter which one it is. Let's do Kz. Again, it doesn't matter. It looks the same regardless. And so now what's happening is that our K vector can only point to certain discrete spots in this space. All right, so for example, there's a spot here at 2 pi over L. There's a spot here at 2 times 2 pi over L. There's a spot here at 3 times 2 pi over L, so on and so forth. All right, so that's along Kx, and same deal along Kz. So what happens is that you get a grid of allowed values. All right, and I think that's enough. All right. Actually, it occurs to me that that probably is not correct. You can't get those values because the integers have to be greater than 0, right? So you get a set of points that look like that. Okay, so what we have is a regular grid of allowed values. And so our K vector can only point to one of these points. So for example, I could get this, or I could get this, but I cannot get something in between. No, 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 bad. You can only have K vectors that point at one of these discrete points on this grid. Okay, so now what we have to do is to incorporate that fact into our calculation of a number of states in a phase space volume. All right, so how are we going to do that? So let's do this by, first of all, calculating, so what is the average density of points? Okay, or similarly states. All right, so each point corresponds to a state. And now what we want to know is what is the density of states inside this phase space. All right, so now what I'm going to do is essentially what I'm going to do is split up the space such that each point occupies an equal volume. All right, so in other words, between each of the points, what I'm going to do is draw a line like this. Okay, and what I'm going to say is that inside each of those boxes belongs to that state. All right, so for example, this state right here, the phase space volume that it occupies is this box. Okay, does that make sense? And you can see what the dimensions of the box are, right? So the width of this box is just 2 pi over L, and the height of this box is just 2 pi over L. And there'll also be another dimension coming in out of the screen that also has width 2 pi over L. All right, so in other words, the density of points in this space, each state, one state, occupies a phase space volume of 2 pi over L cubed. All right, so this is equal to L over 2 pi cubed, or V over 8 pi cubed. All right, so this is just, you know, essentially the 1 point. So again, it's obvious what I'm doing. I'm just taking every point divided by the volume that that point has to itself. That tells us the density of points. All right, everybody cool so far? All right, so now what we're going to do is say that the box that we're talking about is macroscopic. All right, so we have a box of gas, and we can see the box, right? And that means, you know, quantum mechanical particles are very small by their very quantum mechanical nature. And therefore, if we're able to actually macroscopically see the box is much, much bigger than the particles. All right, so if the box is extremely large, which it is, i.e. L is very, very big, okay, then you can see that, you know, the width, the spacing between each of these grid lines is inversely proportional to L. So the larger L gets, the finer and finer this grid spacing is going to be. Okay, so if the box is extremely large, the grid spacing is extremely fine. All right, and in particular, because we're going to assume that the box is macroscopic, what that allows us to do is essentially assume or make the approximation that the grid is continuous. All right, so the grid is approximately continuous. And what that allows us to do is to actually perform integrals instead of silly discrete sums. Okay, so in other words, if I look at a volume of phase space, the number of states within volume V is just going to be equal to that volume V times the density. Okay, and again, this comes from the fact that we're assuming that the density is just a smooth continuous, or approximately a smooth continuous function whose value is equal to this. Okay, and so to get the number of states, we simply take our smooth continuous density and multiply by the volume that we're interested in. Okay, so is everybody cool so far? Or a better question, again, because nobody wants to talk, is anybody not okay so far? Okay, so now what we're going to do is throw in some particles, okay? And again, we have two kinds of particles we can choose from. We have fermions and we have bosons. All right, and so what we're going to try first of all is throwing in some bosons. So let's see what happens. If the particles are bosons. All right, and we're going to talk about a very particular type of bosons, specifically. Let's assume they are photons. Okay, so photons have spin 1. Okay. They also, so you guys know how, you have an intuitive understanding of how photons behave, right? So you have an excited atom, and when it falls, when it, you know, falls out of its excited state, it produces a photon. All right, so you went from 0 photons to 1 photon. And in the course of the atom falling down in its energy state and producing that photon, it did not cost any energy to produce the photon. All right, so what I mean by that is, let's say I have an atom that's, for example, that makes up the walls of the box. All right, and let's say that this atom has 2 energy levels. Okay, these 2 energy levels are a distance delta E apart. If the atom is in the excited state, and it falls down to the ground state, it will emit a photon. All right, and the energy of that photon is exactly equal to the difference in the energy states of the atom. Okay, in other words, it does not cost energy to emit or absorb a photon. Okay, so what does that mean? So now the energy that it takes to either add or remove a particle from your system, that is the definition of the chemical potential, right? So the chemical potential is the energy cost to add or remove a particle from your system. That is what the chemical potential is. Now, because it does not cost any energy to emit or absorb a photon, that means that for photons, the chemical potential is 0. Okay. So we have their spin 1, they have 0 chemical potential. We also know a few other things about them. Okay, we know that the energy of a photon is equal to its frequency times Planck's constant, or written in terms of h bar, this is h bar omega. All right. Okay, now we also know that because photons are the particle of the electromagnetic wave, that they also obey C is equal to their wavelength times their frequency. And again, you can also express this as omega over K. All right, so now K, remember this is the important variable that appeared in our previous discussion as to how to calculate the number of available states to us. All right, so this relationship, which is just fundamental nature of waves, also tells us that K is equal to 1 over C omega. And similarly, dk, if we take the differential of this, it's equal to 1 over C d omega. All right, so these are our fundamental properties of photons. All right, so now what we're going to do is we're going to take a box, again, just like we had previously. We're going to, our box is going to be full of photons. And what we are going to get is essentially, what we want to wind up with is the number of photons in each available energy level. That is the distribution of photon energies inside this box. Does that sound familiar to anybody? What is it we're going to find here? So it's a box full of photons, and we want to know the energy distribution of the box, of the photons in the box. Anybody want to take a guess what that is?
Density of states?
That is, we will be calculating that, but so I'll just give you the answer. What we're going to derive is the Planck black body radiation formula. All right, so Planck's black body radiation formula, it is literally, if you have a box and you heat that box up to some temperature, what's going to happen is that the molecules in the wall of the box are going to get excited and start glowing, right? And so when an object starts glowing as a result of its temperature, it emits a collection of photons at different frequencies or energies. And the distribution of the photon energies inside that box is black body radiation. That's what black body radiation is. It's just the energy distribution of photons being produced from a glowing object. All right. So let's do it. So given these properties of photons, let's calculate the average occupation of each energy level in the box. that is. Well, so this will sound familiar to you in a moment. And then we'll get the total energy distribution, which is the black-body radiation formula. All right, so here's the question we're going to ask. For a given frequency, and again, frequency and energy are essentially the same thing. They're just proportional to one another. So for a given frequency or energy, how many possible states are there? All right, and so our plan, again, what we've got is we have some k vector. All right, so k vector, and every equal length k vector gives you the same energy. So our states that we're interested in are going to live on a sphere. Okay, and again, to allow us to actually, what we want to do is to take a volume in this phase space and multiply it by a density. All right, and that will give us the number of states that we're interested in. All right, so what we're going to do is we have our, well, let's not overcomplicate this drawing. We got this sphere. The sphere has surface area of 4 pi r squared, right? The radius in this case is k. All right, and then what we're going to do is we're going to kick the radius out by a little bit to give us a spherical shell. All right, and we're going to kick it out by an amount dk. All right, so the volume in this region which I will call dV. It's an infinitesimal volume because it has an infinitesimal thickness. So I will call this dV is equal to the surface area times the distance we kick it out, dk. All right, that's pretty straightforward, I think. Now what I want to do is, again, we want to express this in terms of frequencies, not k's. All right, so now what I want to do is to take this and rewrite it in terms of omega instead of k. All right, so what I'm going to use is this. K is equal to omega over c. And hence, this is the same thing as 4 pi k squared over c squared. And then what I'm going to do is the chain rule. All right, so I'm going to replace dk as dk over d omega. All right, so that's just the chain rule. Now, what is dk over d omega? From here, we can see that dk over d omega is equal to 1 over c. Right? So we can write this as 4 pi omega squared over c cubed d omega. So that is the volume of my infinitesimal shell in phase space. Okay, so that's the volume. Now we want the number of states. So the number of states, okay, is equal to, by definition, is equal to the density of states, which I will call g of omega, times d omega. I wrote that chose a very poor place to write that. This is the density of states. And that is essentially what we are after. Okay, so the number of states is equal, by definition, equal to the density of states times d omega. And again, we go back to this argument that we made right here, that it should also be equal to the density of our grid times the volume and phase space that we're talking about. All right, so we take that. So this should also be equal to dV times rho. Now, right here, we just got an expression for what dV looks like for photons. All right, so dV for photons is 4 pi omega squared over c cubed d omega. And rho is this thing we derived up here. All right, so rho is V over 8 pi cubed. All right, so we just algebraically massage, and we get V omega squared over pi squared c cubed d omega. We compare that to this, our definition of the density of states. So you can see the d omega is here, the d omega is here. That means that this jobby right here is our density of states. All right, so we have our density of states is equal to V omega squared over pi squared c cubed. All right, now we have to take something into account. Oh, wait, I'm sorry. I lost a factor of 2 somewhere. 2. All right, now we got to go back up here to right here. Photons have spin. Okay, and where that manifests itself when you're actually looking at light is the polarization state. Okay, and so just like electrons have 2 possible spin orientations, photons also have different polarization states. Specifically, they have 2 polarization states. They have left-handed and right-handed circular polarization. All right, so photons have 2 polarization states. Left and right-handed. I believe the particle physicists refer to this as their helicity. Okay, and what that means is that for every one of those points in our grid, in our phase space, each one of those points is actually 2 points on top of each other, because one corresponds to left-handed circularly polarized light and the other one corresponds to right-handed circularly polarized light. So in other words, the actual density of states is actually twice this number. All right. So in order to take our polarization into account, our density of states is actually V omega squared over pi squared c cubed. All right, so that is our density of states. All right, everybody with me? All right, very good. So now the next thing we take into account is the fact that photons are bosons. Which means that they obey Bose-Einstein statistics. That is, their average occupation number in each available energy level is equal to 1 over e to the beta epsilon and minus mu minus 1. Again, remembering that our chemical potential for photons is 0, and hence that simplifies this even further. It's just beta epsilon. Okay, so now what we're going to write is the number of photons within a frequency d omega is equal to the number of states available to them times the number of bosons per state. Okay, this is what we just calculated up here. This is g of omega d omega. And the number of bosons per state, this is our Bose-Einstein distribution. Okay, so the number of photons within a frequency d omega is equal to g of omega d omega over e to the beta epsilon minus 1. Okay. Now, finally, the energy. So now the problem is the numerator is expressed in terms of omega, and the denominator is expressed in terms of energy. So now what we want to do is express the energy in terms of omega. All right, so the energy per photon is, we all know that, it's just h bar omega. So you just plug that in there for E. And what you get is that E of omega is equal to h bar omega g of omega d omega over e to the beta h bar omega minus 1. And again, this right here, this is the number of photons. And each photon has energy h bar omega. So that's where this extra h bar omega is coming from. So we just take the energy per photon times the number of photons. That gives us the amount of energy at that frequency. Okay, now we just plug in what g of omega is. All right, so now we just plug in our result for g of omega d omega. And we get ta-da! This is Planck's blackbody radiation distribution. Okay, so this formula is what made Planck into, you know, one of the venerable legends of our field, right? Is that he came up with this formula. Although he didn't come up with it this way, he just came up with he got it another way by assuming that energies are quanta. He went through some other labored derivation, which ultimately is the same as what we just went through. All right, although ours was grounded firmly in quantum mechanics and statistical mechanics. All right, now the last, so in other words, a box full of bosons with zero chemical potential, that is photons, their energy distribution is Planck's blackbody radiation formula. The last thing I want to show you is that at low frequency, okay, then e to the beta h bar omega minus 1 is, if the frequency is low, that means the exponent up here is very small, and you can therefore Taylor expand, everybody's favorite trick. So if you Taylor expand that exponential, you get 1 plus beta h bar omega minus 1. Okay, so this is equal to just beta h bar omega. Okay, so now you make this substitution back into here, and what you get is that E of omega is approximately equal to V times kBt over pi squared c cubed omega squared. And this is our old buddy Raleigh Jeans. So this was what people got before they introduced quantum mechanics. For black body radiation. Okay, so when you make the assumption that you are at a low frequency, that is low energy, okay, then you recover the Raleigh Jeans formula. Okay, so I think that's it for today. So does anybody have any questions? So now you might ask why at low energy does that recover Raleigh Jeans formula? So now, so what we're talking about is low energy per photon. So the quantum nature of photons becomes more apparent when each photon has really high energy. So when each photon has really high energy, you can feel each one of them smack into you like a tennis ball in the face. But when they have low energy and you just have a whole bunch of photons that are, it's like a light rain on you. It's like a smooth, continuous rain of photons. So in other words, it approximates Maxwell's equations. And so with the approximation that the field is behaving like, or the photons are behaving like Maxwell's field, then you get the continuous Raleigh Jeans formula for black body radiation. Okay, I'm out of time. I've talked too long. So does anybody have any questions? All right, so what we're going to do on Friday is we're going to talk what happens when these are material particles. That is, particles who do not have zero chemical potential, things like helium-4. And we put a bunch of helium-4 into a box, and what we're going to learn on Friday is that they Bose-Einstein condense at low temperatures. Until then, my good folks, I will see you on Friday.